Hey everyone, so we're DGAL, Distributed Genetic Algorithm Library. I'm Paul.
I'm Chris.
I'm Colin.
And so basically, our project focuses on the concept of genetic algorithms, which basically models evolution. It starts out by generating a whole bunch of random solutions. We call those individuals, like individuals in a population, if you learn about in biology. And we have to generate a fitness level based on certain parameters, and those most fit individuals will be passed on to the next generation, and it goes under an evolution-like process to determine the most fit solution at the end.
All right, so our project, basically, we're trying to streamline this so that you just basically plug in a fitness function and then it'll run it, and it'll actually, there's two parts to our project. The first is the actual, like on a local, like a population of individuals where we're finding it, the genetic algorithm, and then we're distributing it where we're actually running this algorithm on multiple different nodes, if you will. And so I guess we worked on the local side, and then Colin will go into the distributed side after that. But basically what I've been working on right now is finding a choose parents function, and basically what I'm doing is I'm trying to find like the most fit, but like when you're doing natural selection, you can't just pick like the top best fit one every time, because then there won't be any diversity, and then you only have that trait essentially. Like if you're think of like, you know, say a squirrel and they're reproducing, if you only use the same squirrel every time, then you're only going to have that in your population. You want diversity to find the best one. So basically you're finding an algorithm finds like the top half, I guess you could say. Like it's got to be random enough where there's enough diversity. And so there's a bunch of different algorithms. There's like a roulette wheel selection where you're basically totaling all the fitnesses, and then you pick a random number, and then you're just finding once that you like go through your vector, I guess, of pointers which would to each individual, and you're taking the fitnesses until it totals up to greater than that random number, as well as you can compare. Use like tournament selection where you're comparing a group of you're taking two individuals randomly and picking the best one and then repeating that process.
Yeah, and then I've been determining when to kill each node. So whether that node has reached a certain number of generations, it's run for so long, or it's gotten the desired fitness level, and then those nodes will eventually communicate to see which of the nodes have the highest fitness level, which ones need to restart, and so on.
So I've been working on basically the distributed part in the server that handles all the communication between them. So you can see here we have the coordination server, which just keeps track of all the nodes in the network. And you can see there's 4 different nodes here. Node 1 has the current best fitness, and the other ones are lagging behind. And because because we have this coordination server that knows about all these nodes, we can actually send out, we can have node 1 tell the coordination server about this, and it will send out that information to the other ones. So now all of them are working with the best individual that we have as well right now. And we want to do this because we don't want a bunch of the nodes in the network to be working on a solution that's suboptimal if we already know that we already have something that works much better. So this is just kind of a way to sync everything up while still maintaining the ability for different nodes to work on different individuals, because it'll only sync maybe the best 2 or 3 individuals from one of the nodes, whereas they could be working on hundreds of individuals at a time. So it's a way for us to tell these nodes that, hey, there is something better, but continue working as you would, and we'll just throw this individual in with you. So a lot of you may have been here for RCOS last semester, and I had this project started last semester. There's been a couple changes to it. First of all, we dropped Windows because Windows sucks. Because the C++, we are trying to use no external dependencies except for the C++ 11 standard, and too many of the compilers in Windows do not support the full feature set of C++ 11. So like even stupid stuff like toString is not supported in Cygwin or VCC, at least not the versions that I was using. So possibly after more of the project is complete, we can add in Windows support again. And another change is there's no peer-to-peer connection for certain communications. So we had a ring communication where instead of one server sending it to one node sending to the server and the server sending it out to everybody, it was going to directly connect to each of the nodes in a ring pattern. But because firewalls are annoying, we got rid of that for now. At least the peer-to-peer communication-wise. We might have the server still do somewhat ring, but right now, because firewalls are preventing us from opening up ports and it's just annoying, we're gonna axe the peer-to-peer communication until later on. So I just have a quick little demo for. That's big enough. So I'm just going to start up two different nodes in the network here, and so it'll run through these generations, and you'll see that some of the best individuals will be transferred over to the other node that's running, if you can read it quick enough. So this just ensures that we don't have one of the nodes using useless individuals, because otherwise the one on the right over here could have gotten stuck at trying to calculate nodes that are working on a fitness of 5, whereas the other one's working at 47. So they're the exact same. The top two now are actually the exact same on both of the nodes, minus some rounding errors from transferring doubles over a network. But that's pretty much the gist of when the nodes are running, how it'll work out. And to actually create an individual, we're trying to make this as easy as possible. So to actually create an individual, you simply have to extend the DGAL individual class right here, and you can see there's really not much to it. I defined a print class, and you really only have to define a run and serialize and create from serialized, and that's all you have to do. And this is because these types of algorithms are used in like scientific research, and a lot of scientists don't really know how to program, so as little as they have to do, the better. So we're trying to make sure that everything is simple. Essentially, what I want to do is I want to completely even remove the serialize functions, so that they don't even have to worry about that. But as of right now, this is how it is, and you can see like this fitness function, this run fitness function is kind of just a BS one that I made for the example, but it's really just simple. You just have to input, some basic algorithm to calculate your fitness, and it just does everything else for you.
What's the array of values at the top?
That was just for the demonstration. It's really just a pointless array. So yeah, that's pretty much it. So questions?
Yeah. For the fitness algorithms, does it take into account things like reciprocal altruism and kin selection,
whatever would have to, if you needed it for your simulation and you knew how to implement it, you could do it.
Okay.
So fitness function, we are trying to stay out of the fitness function as much as possible and let that be mandated by whoever's using this library. The whole point of this is that we're not trying to force anything on you. We're just trying to make it easy for you to make these algorithms.
I thought that the point of genetic algorithms wasn't for biological simulations, but for as a sort of a generic search procedure. Is that correct?
I mean, it can be used for a whole bunch of different things. I can't speak to exactly what a lot of people are going to be using it for. It's going to be up to them. But I mean, I know for us, at RPI, if you took proglang with Rally, you used a genetic algorithm to figure out the knapsack problem.
Okay.
You know, it can be used
So
for a
in that
whole
case,
range
it's
of different
used
things.
for
It's just,
optimization problem.
Yeah.
Searching over. Okay.
so, anything else?
Are you allowed to, so is the actual genetic algorithm that, given a list of individuals in the fitness selects the best, or selects the new individuals to pump out, are you going to make that customizable at all, either through parameters or
So-
through extending it?
So we do have a base, a population, so to say, which is the controller for the whole like generation and creating new generations. And right now, that is pretty much all extendable. So you can overwrite most of those things. But if you didn't want to, it's already got a model in there for you to just kind of run with. But yes, everything is extendable and customizable if you wanted to tweak how it ran specifically under the hood.
What parts of C++ 11 do you want in particular? I'm just curious.
So for the server, C++ 11 we're using a lot of threading. Even with the clients, we're using a lot of threading. We're doing a lot of work with Lambda functions and stuff like that. But even like I said, toString on Cygwin doesn't work for C++ 11, at least with the version of GCC that we were using. So I mean, it's not that like the major features that we want to use are kind of there, but there's some small stuff that's causing compile errors, and I just didn't want to deal with it at the time, so I said Linux only for now. So.
I'm pretty sure that Cygwin is like a full POSIX compliant system, and I think it would be as simple as configure, make, and make install to get the newest version of GCC.
I had installed GCC from Cygwin's repository, and it was the same version as the one on my Linux system, and
Okay.
it still did not match up properly when trying to compile.
Okay.
Anything else? All right. Thanks, Steve.